Good morning. In the last class we talked about the word detonation, and what did we tell? Supposing we have an explosive gas mixture in, let us say, a container, and instead of igniting it, and how do we ignite? We deposit some heat source, like a spark, something which is hot. The heat from the source goes and heats the neighboring gases, and chemical reactions occur. It heats the neighboring gases and so on. A flame, maximum velocities are of the order of a meter per second. That is the rate at which the flame propagates out. If the same energy or some energy is deposited, let us say, impulsively. By impulsively, what is it I mean? Sort of spontaneously, that is over a very short period of time, and we have already learnt about it. When some energy is deposited in a medium spontaneously, what happens is a shock wave gets generated, and this shock wave keeps decaying with distance. Like for instance, I form a shock wave of a Mach number ms. This is at point 0, maybe at point O, which is the 0th scale over here. X axis is the distance. The Mach number keeps decreasing with respect to time. And we told ourselves, well, a shock wave is formed under certain conditions if some energy is deposited impulsively, and if chemical reactions, if the shock wave propagates, let us say, in the same explosive medium in which a flame propagates, what is going to happen? You are going to have chemical reactions taking place behind the shock wave, and this chemical reaction is something like which is energizing the shock wave, and this shock wave actually decays with time because some dissipation is happening, some expansion processes are happening behind the shock wave. Because of that, the Mach number decreases. But if this energy balance or the chemical energy which is released is able to overcome this decaying influence, well, instead of the Mach number decaying, well, it could move at a constant velocity. That means I have a shock wave which is moving at a speed greater than the sound speed, and mind you, the pressure density increased behind the shock wave. This increased pressure, the increased density is now propagating at supersonic speed, and this is what we call as a detonation. That means a shock wave induces chemical reactions, and this chemical reactions in turn drives the shock wave, and this particular sequence, namely a shock forms chemical reactions behind it, and this chemical reactions drive the shock in turn, is what we call as a detonation. A detonation can propagate under steady conditions provided the losses incurred by the shock, let us say the blast wave due to expansion behind it, maybe due to the dissipation effects. If the energy release can overcome this, it can travel at a constant speed, let us say d meters per second. This d meters per second happens to be a large number because shock by itself travels at a high velocity greater than sonic speed, and if by chemical reactions it can be made to travel even faster, and therefore what is going to happen? Let us redraw our figure now. You have ms, that is the Mach number of the shock as a function of Rs. You have a blast wave which is being formed, it keeps decaying with distance. Let us say by some distance I am able to form sufficient chemical reactions, and let us say it is able to form a shock wave which is travelling at a given Mach number, and this is what is a detonation. That means till here you have a decaying shock wave, the decaying influence is overcome by chemical energy release, and you get a detonation. Therefore, a detonation is a combination of a shock which induces chemical reactions, and this chemical reaction in turn drives the shock, and this constant velocity is often spoken of as Chapman-Jouguet velocity. We will come back to it. Now, if we are very clear, therefore, now we say, well, a detonation is a shock wave in which maybe chemical reactions are induced, and the combination of the shock with chemical reactions is what we call as a detonation. I think we have to be a little more clear about it, and we have to distinguish it from a flame. Well, in a flame, it is the transport of heat, transport of concentration from the source which really propagates a flame. That means something heats it, you have something like an ignition kernel, and this kernel must be of some minimum size such that the heat loss within it is able to is able to cause chemical reactions in the adjacent layer without itself collapsing. We said ignition kernel size must be greater than the quenching distance. So, also can we say something about the energy requirements to form a detonation? Mind you, we are very clear these are two different things altogether. In a mixture which is, let us say, an explosive gas mixture, or you have an explosive substance like, let us say, TNT or some liquid explosive, I could form, when the energy is liberated slowly, I could form something like a flame which travels at maximum a few meters per second. I could also form a shock wave in which chemical reactions occur behind the shock wave, and I could form a detonation. Principally, both are totally different in that this is compression, because behind a shock wave you have compression. In this case, we found it was an expansion. Therefore, these two things are totally different. But let us go back and find ourselves, if I can imagine something like an ignition kernel for forming a flame, and we know how to estimate the minimum ignition energy, can I go ahead and write out what is required to form a detonation? What energy release is there? If the energy release is, let us say, impulsive or spontaneous, how much energy is required? Let us go back, let us address this problem. It is quite simple, and what we say is, well, now I say I deposit some energy E naught in a particular medium, and what happens? A blast wave is generated, let us say, along the distance Rs. It could be any direction. We again confine ourselves to assumptions that we are talking in terms of a spherical wave which propagates out, and we say, well, I deposit E0 joules over here. Well, I say I have already done this problem as regards the blast wave formation is concerned. I have already done this earlier, and what did we find? The Mach number of the blast wave is related when the wave is strong. Mind you, I do need a strong wave because I want chemical reactions to occur behind it. I know that yes, ms square is equal to 1 over 4 pi I into gamma into 1 over Rs by R naught cubed, where R naught is the explosion length R naught, which we defined as E naught by P naught to the power 1 by 3. Therefore, according to this, well, I have drawn this earlier, again I draw it, let us say ms as a function of Rs by R naught. What is going to happen? It is going to keep decaying with respect to time. But now we tell this energy is deposited in an explosive medium which can sort of burn, and therefore, what is going to happen? Well, I have the shock. Initially the shock is strong, the shock keeps decaying in strength, maybe initially the Mach number may be 8, 5, 6 and so on. It ultimately decays to an acoustic wave, and in these regions I know how to estimate the temperature behind the shock front. Let us estimate one or two cases. We know, well, the density behind the shock to the density ahead of the shock. If we go back and just check ourselves, we know S is equal to gamma plus 1, where gamma is the specific heat ratio, gamma minus 1 plus 2 over ms square plus 2 over ms square. We will forget this because we are talking of a strong shock solution. We say, well, I want high temperatures, therefore, I am really not looking at the value of the Mach number, because the Mach numbers are high. 2 over ms square is equal to gamma minus 1. Let us put it down, 2 over ms square is large, therefore, 2 over ms square is small compared to this number, therefore, I can write it as gamma plus 1 divided by gamma minus 1. Similarly, I write that the pressure behind the shock divided by the initial pressure of the medium. Mind you, I say that the pressure of the explosive gas is P naught, the density is rho naught, the temperature is T naught to begin with, it is unburned medium. I can write it as equal to, we again go back to gamma plus 1 into the Mach number square minus, you had gamma minus 1 divided by gamma plus 1, and we said, well, for shock, this is a strong shock, for ms being large, this is small, for ms being large, this is small. Using these ratios of the density, let us say, what did we say therefore? We could create a blast wave. Behind the blast wave, I am able to estimate the density, I am able to estimate the pressure behind it. Using these two relations and using the gas equation P is equal to rho RT, I get that the temperature behind the shock to the temperature ahead of the shock is equal to, it is ambient temperature, let us say 300 Kelvin. I can write it as equal to Ps by P naught into rho naught by rho s, and I can estimate the temperature using these two expressions. I put one on top of the other, and for a temperature T naught, for the different values of Ms over here, let us say typically strong values, let us say yes, I consider the Ms values, I can estimate the values, and let us put these values in the form of a small table over here. What is it I am going to plot? I am going to plot Mach number Ms and how the temperature behind the shock changes. Well, if I consider a somewhat weak shock, let us say the temperature behind the shock. If I consider, let us say, a weak shock, and what is it I get? I get, if the shock is weak, let us say 2, the temperature estimated for Ms is the only variable, for air gamma is equal to 1.4, the temperature is around 500 Kelvin. When the Mach number of the shock is 3, the temperature is 805. When the Mach number is 4, Ms is 4, the value is 1210 Kelvin. When the value is 5, the Mach number is 5, the temperature is 1740 Kelvin, and the last one, let us say at a value of 6, Mach number is 6, the temperature is 2385. We know that when the temperature rises to a value around 1500 to 1600, you have auto ignition of the gases taking place, and therefore, I can say, well, if the Mach number of my shock is such that its value is greater than between 4 to 5, let us say, then chemical reactions will spontaneously occur behind it. Therefore, if I were to generate a shock whose Mach number is, let us say, greater than around 4, that means greater than this limit, well, I can form a detonation. I will tell myself, well, there should be something like a critical Mach number, which I can say is Ms star critical, and it is the duty of the energy which is liberated should be able to form a shock whose Mach number is, let us say, greater than equal to between 4 to 5. In most explosive gas mixture, if I have an explosive gas mixture which auto ignites at let us say 1000, then it could be between 3 and 4. If I have an explosive gas mixture which is so inert or something which does not ignite spontaneously, but which ignites only around 2300, well, the Mach number should be 6, and therefore, maybe on an average it is between 4 to 5, and therefore, I can tell myself the duty of the ignition source is to generate a Mach number which is greater than this. But how do I do this? I would like to define something like we were able to say, when I have a flame, what did I tell? Well, I wanted an ignition kernel. I wanted a kernel of flame, an ignition kernel whose size must be greater than or equal to the quenching distance for a flame to get started. Can I also say for a detonation, what is that minimum volume? Can I talk in terms of a detonation kernel or a seed which is required, detonation kernel, which is required to start off a detonation? And if so, can I say what must be the minimum size of this? Just like I say, minimum size of a flame kernel is the quenching distance, what should be the minimum size required? And I would like to spend some 3 or 4 minutes on this, because this will give us an idea on what are the type of energy which is required, and we will be able to calculate the energy required for a detonation to form. Therefore, let us spend some 10 minutes on this or 5 minutes on this and try to proceed further. Well, we have already said the Mach number, in case I am talking of a medium which is not explosive, let us again put a medium over here. This medium, to begin with, let us say it is at an initial pressure P naught, density rho naught, temperature T naught, and let us say it is inert. And therefore, I know that the Mach number of the shock which is generated, I just wrote the expression, let us write it again, 1 over 4 pi I we said is an integral constant which denotes the ratio of the kinetic energy of the shock medium divided by the kinetic energy if the entire medium were to move at the shock speed, 4 pi I gamma into 1 over Rs by R naught cube. But here I also have the explosion length, and I am interested in some energy which is liberated E0. If I want to put E0 explicitly and I want to form the value of Ms as a function of only Rs and not Rs by R naught, for different values of the energy release E naught, well, for one value I get a curve over here. I increase the E naught significantly and then I get another curve over here. If I increase the E naught still more, I get the third curve over here. Therefore, the direction over here is in the direction of E naught joules over here. Therefore, this is how a blast wave decays as it is formed by energy release in an inert medium. Now, I make this into an explosive medium, and this explosive medium has a say, let us say, same pressure, same initial pressure, 1 atmosphere pressure, same initial density and the same initial temperature, let us say 300 Kelvin or so. And now what is going to happen? Well, a strong shock is formed, let us say the level I am considering energy release corresponding to the white line over here. And what is going to happen? Well, as it propagates out, now the shock is strong. Let us say the Mach number I denote Ms star, which corresponds to rapid auto ignition of the gases behind the shock. I form a shock wave. The temperature behind it is Ts. We have already estimated the value of Ts. We said Ms is between 4 and 5 and the temperature here is quite large such that chemical reactions are occurring. Therefore, in this particular zone of gases which are above this, I expect chemical reactions to occur behind the shock for all these three cases. White line, maybe the particular line here, maybe the line over here. But now, if I say, well, these chemical reactions, however spontaneously they occur, will take some time to take place. That means, even though I create a shock wave, the time for chemical reactions is not instantaneous. It will take, let us say, a microseconds, maybe 10 microseconds, or let us say a millisecond. Therefore, this will take place only when the shock has travelled a particular distance. That means, by the time a particular, that means a blast wave is formed, it travels a particular distance from the source, and by the time it travels a particular distance, maybe the chemical reactions should have started taking place, because we say, well, there is a characteristic chemical reaction time, and mind you, in addition to characteristic chemical reaction time, we found that there is a large induction time. Mind you, let's again go through this. We told ourselves for most of the explosives the activation energy is large, and how does the chemical reactions occur with respect to time? Let us say this is the energy release. Initially there is an induction time in which the chemical reactions get ready, chains are formed, and once the chains are formed I have a rapid one. That means I have something like an induction time which we call as induction time followed by the chemical reaction time, and this is going to take some time, and therefore, maybe by the time the shock travels at certain distance, the induction time should be over, so that the chemical energy gets released and the shock, that means there is a need to have a minimum value of Rs star. That means a minimum distance, and this minimum distance perhaps could correspond to what we are looking for, namely a detonation kernel. I think we are still not too clear about it, but let's presume that yes, the chemical energy must be released in the medium by the time the shock, because if the shock, let us say if we take another instance, if the shock were to decay to this particular value, well, below this the chemical reactions just take too long a time, well, the shock cannot really convert to a detonation. Therefore, by the time the shock strength reduces to a critical value Ms star, it should have moved a particular minimum distance which I can call as a detonation kernel. Maybe I have to refresh this definition again, but for the present I say it must move a minimum distance away, and this minimum distance away is necessary to form a kernel of explosive gases. Therefore, let us write an expression for this, for the energy release, and then let us put things together and view it in the light of some experimental results such that we can formulate a criterion for starting a detonation or initiating a detonation. Therefore, let us now presume, yes, I have a blast wave. Let us presume, yes, I have a blast wave which is formed of some size Rs. Let us say the distance from the source is Rs. As usual, we make the same assumption, rho naught is the density and all that. We also presume that the Mach number of this blast wave when it is at a distance Rs is such that the value of Ms is greater than between 4 or around between 4 and 5, such that chemical reactions take place behind it. That is, it is chemical reactions are taking place in this particular medium. Because the blast wave is strong, we say, well, the time of the distance travelled is such that the chemical reactions have taken place. Let us presume, well, this is filled with chemical reactions, and if it is filled with chemical reactions, the chemical energy what is available within the blast wave, chemical energy which is available is equal to the volume. What is the volume? 4 upon 3 pi into Rs cube, this is the volume, into the density which is the mass, into the chemical energy which is released. Let us say Q is so much, let us say joules per kilogram is the chemical energy what is available over here. What does this chemical energy do? It increases the temperature of this medium, that is the internal energy of this medium. It also increases the kinetic energy because the shock is moving, it supplies some velocity to the flow field. Therefore, this chemical energy gets translated. We are not really considering now the effect of the initiation energy, we are considering separately. We are considering just the effect of the chemical energy, and what does it do? It increases the kinetic energy, and that is we look at a small segment over here. Let us say a particular shell, a spherical shell whose density should be rho, whose velocity could be u, whose temperature could be T. We have been writing this in whenever we talked in terms of blast waves, and therefore, we say this is equal to integral of 0 to Rs of the internal energy plus the kinetic energy over this particular medium, that is dm over here, and dm, which I can again write it as equal to the surface area of this particular thing, let us say 4 pi r square into dr into rho over here. We have derived this expression, we have derived what this particular limit is, and what did we derive it as equal to? I could write internal energy as CVT, kinetic energy is equal to u square by 2, and therefore, I have therefore rho u squared, this became p over gamma, therefore, p over gamma minus 1 into rho, and therefore, rho and rho got cancelled, and we got this final expression as equal to I, that is integral, let me put it separately, 4 pi into we got Rs cubed into Rs dot square into I over here, and what was the value of I? We said I is an integral is equal to 0 to 1 of f over gamma minus 1, that is the pressure, into density of we had something like psi phi square divided by 2 into we had r by Rs into d eta. You will recall we said that this integral is around 0.423 or something for a medium like air. Therefore, we are able to get this relation, that is 4 pi Rs cubed into Rs dot square into I, and this comes from this particular expression, and therefore, this is equal to this particular value, and therefore, what is it I find? Mind you, here rho by rho naught, I should have got a rho naught also over here, and therefore, when I equate these two expressions, what is it I get? 4 upon 3 pi, whatever I have written here, Rs cubed into rho naught into q is equal to 4 pi Rs cubed into rho 0 coming over here Rs dot square into I, where I is the integral constant. Therefore, I find 4 pi cancels on both sides, rho 0 and rho 0 gets cancelled, Rs cubed gets cancelled over here, and I get the value of Rs dot square is equal to, I simply get it as q divided by 3 into the integral particular expression. And now, if I want to write it in terms of Mach number square, I know Mach number of the shock front behind which chemical reactions are occurring is equal to Rs dot divided by A0, or rather I get Ms square is equal to q divided by 3I into A0 square, where A0 we said is around 330 meters per second. Therefore, this is from the chemical reactions what is taking place. Well, the blast, when no chemical reactions are taking place, it goes as per this particular expression, And combining these two together, can I now say what is the value of the detonation kernel or the kernel of gas which can really form a detonation? Therefore, now I put these two things together. Well, I say I have ms square from as a function of Rs for a given value of energy release, and what happens? Well, the blast wave decays in an unreactive medium like this. When the medium gets to be reactive, and provided I have sufficient quantity, that means the time is sufficient for energy to get released, well, the ms square could be something like this. This is for a detonation velocity that is equal to the value of m from the chemical energy release. This is from the decaying influence of a shock wave. That means the chemical reactions must be able to overcome the decaying influence of the shock wave, and when the chemical energy release overcomes the decaying influence, what is going to happen? Well, it comes like this and gets into a shock, and therefore, I can tell that, well, the role of the energy release is initially to form a decaying shock wave, but if the decaying shock wave is greater than some limit, well, it gets into this and forms what we call as a detonation. Therefore, on this plot, now I say, well, I want to include the different values of energy release, and let us see how it will look like. If I have a very small energy release, well, it goes like this. Well, by the time the critical distance is required to release the chemical energy, the shock has decayed to a very low value. Well, it cannot initiate. Well, if the energy is very large, well, it can directly release the energy and it goes into a detonation. On the other way, in the extreme case, that means this is E naught large, well, the energy release is very small. Under some critical condition, it is possible that the energy release, as I have sketched by the orange line, it comes to the ms value, energy release takes over and drives a detonation, and this is how we should be able to imagine or maybe have a think model on how to form a detonation. Therefore, to form a detonation, I summarize here by saying it is necessary to form, let us say, a detonation kernel. I still use the word kernel because we are very clear about it in case of a flame, and this kernel size should be a minimum volume, let us say Rs star, and this Rs star must be formed by the time the shock decays to a critical strength ms, and this Rs star at the value of ms star is what we could call as a detonation kernel. And once I know a kernel volume, I can always find out what is the energy which forms this kernel, and I can find out my energy release. Therefore, before going further on the theoretical grounds, let us take a look at some of the experiments and then calculate the energy release. And I show a few experiment results before going forward, and in the first slide over here, I show some experiments which were done at McGill University in late 60s and early 70s, and what we find is, in this case, a laser spark is used to start a spherical blast wave. The medium used is low pressure acetylene oxygen system, which is diluted with argon again, and what we find is, initially a blast wave is created at a small time, let us say 1.6 microseconds. The shock wave or the blast wave moves forward, it still moves forward at 8 microseconds, and it keeps propagating out. This is the first circle, what you see is the spherical shell of the blast wave which is being formed. In this case it was cylindrical, but let us assume a 2-dimensional geometry, as the first circle is the blast circle, that is the shock circle. Behind the shock, when the temperature is large, chemical reactions occur, and therefore, here you see behind it there is some chemical reactions occurring. The shock weakens, it takes more distance for the chemical reaction to take place. The shock further weakens, you have the shock here, chemical reactions in the second zone. That means the chemical reactions are further occurring away from the shock. That means the chemical reactions are occurring far from the shock, and these chemical reactions cannot go and supply energy to the shock because it is occurring much later. For the chemical reactions to supply energy to the shock, what must happen? Let us take a look at it on the board. All what I am trying to say is, well, let us go back to the streak diagram with which we are familiar, which we studied in the blast waves. You have the temperature axis, time axis, I am sorry, you have the distance axis. Well, the blast wave gets formed like this. In the limit, it becomes a sound wave. Initially, I have strong shock wave, and what happens? A particle entering over here is following the shock wave like this. If the particle takes a long time to burn, well, it is going to burn over here. And since when it burns over here, the blast wave is already here. It is not able to translate its energy here and keep pushing it like a piston moving a wave. Whereas, if the wave is going to, if the shock is sufficiently strong and if it is going to burn right over here, the energy is going to feed into it. Maybe a particle entering here will feed into this and it will push this wave. Therefore, I would like this particular distance, that means this particular distance or this particular distance to be as small as possible, such that chemical energy can really push it. If it is going to burn over here and is going to be say far away from this zone of chemical reactions, well, the energy cannot really push it because it gets into the medium. It cannot really go and push the shock wave like a piston pushing a wave. Therefore, what happens is, in this particular case, the energy release is small and therefore, you find the chemical reactions to decouple from the shock front. Let us go to the next case and examine. In this case, the energy is high. Well, I form a shock here and the chemical reactions are occurring almost at the shock, and therefore, you find, well, this is the case in which I want, the energy is sufficient to form a shock. I also show the case wherein the critical condition, that means initially I form a shock, the chemical reactions occur at some distance away from the shock, therefore, it sort of decouples, but then it really does not decouple like in the first case wherein the distance kept on increasing between the shock and chemical reactions. What happens is, at some particular distance it moves as a quasi steady, that means both are moving together, some instability sort of develop, and therefore, what is happening is the whole thing becomes highly messy and the chemical reactions couple with it and I form a detonation. This seems to correspond to a critical case. I can also show it in a streak picture wherein maybe when you have the shock, that is the blast wave is over here, it travels forward, you have the chemical reaction zone which are over here, chemical reaction zone over here, blast wave over here, the two keep on increasing in distance and therefore, the energy is insufficient to form a detonation kernel of some minimum size. Over here, the energy release is large, I have a strong shock wave, mind you, here the velocity is much higher, chemical reactions occur just at the shock front and drive it as a detonation. This corresponds to the critical case where initially there is a decoupling and then I have both going together and then forming a detonation. Therefore, these experiments are suggestive of the following. Well, I have Mach number versus the distance. If the energy release is low, well, by the time a core of chemical reactions is formed, the shock wave has decayed to low velocities and I really cannot form a detonation. If the energy release is large, E0, we find this is the direction of energy release. If the energy release is large, well, I am able to form a detonation. Under the critical conditions, it seems to decay to a smaller value and then maybe go at a constant speed between the two, there is a constant zone of separation and then it transits into a detonation. We still have to take a look at it, but all what we are saying is when the energy release exceeds a threshold value, I am able to form a detonation and this detonation travels at a constant speed, which we said is known as Chapman-Jouguet speed and which we have to still model it. But we say, well, under certain conditions, well, it decays to a smaller Mach number and under critical conditions and then transits into a detonation. I want to put all these things into a small model and therefore, I first try to say based on experiments and based on the considerations which we discussed before looking at these three experimental results, we say, well, initial phase is maybe due to the energy release, the blast wave decays, and if the energy release is such that I can form a detonation kernel under critical conditions wherein I am just able to maintain the distance between the shock and the chemical reactions to be small wherein they are both quasi steady and the chemical energy can drive the blast wave, well, I can find the critical energy required for a detonation. Under these conditions, I say, well, the distance traveled by the blast before chemical reactions couple is what we call as a detonation kernel. And why do we need this? Well, we need a minimum time for chemical reactions to occur, which we talked as the induction time. You will recall, well, on time, you have the time axis over here, maybe the temperature over here, and what is it we say? Well, the chemical reactions have to take place before the maximum temperatures are reached. Well, this is about the background of the experiments, and therefore, now we can write the expressions down. We found, yes, we wrote an expression for chemical energy release when all the chemical energy is released, but now we find, well, there must be a distance. That means shock is over here, it takes a definite time for chemical reactions to occur. Therefore, when the shock is at distance Rs, I have a distance delta corresponding to the induction distance over which shock travels. This is the chemical energy release. Well, this is the energy release from the source over here, and these two, this plus the initial energy release is the total energy release in the medium, which using the same principles what I illustrated for the source and chemical energy release, I can write that the Mach number of the front, that is the shock wave front, which is generated by the chemical energy release and by the energy release from the source. Now, I put it as Es or E naught over here, is given by this particular expression, and I have the value I coming here. I combine the E naught and Q over here. I said it is also a function of the induction time. It is not Q by 3A naught square, which I just derived on the board. It is also a function of this particular distance over here. And I, we said, is the energy integral, which we studied earlier under blast waves, which is equal to the kinetic energy and internal energy of the shock gases divided by the kinetic energy if the entire mass of gases were to move at the shock speed. Well, this is the formulation of a theory, and let us see what I get. I write the equation again as m square is equal to 1 over I, source energy term over here, the chemical energy term over here. Well, I can even neglect this because the initial internal energy E naught, we have been always neglecting it over a blast wave. It is not necessary to consider. And what is it I now tell myself? Well, the decaying influence of the shock is due to the source. If it was in an inert medium, ms square is equal to 1 over I into this particular source energy term. It decays as Rs cube, and this keeps decaying, and the chemical energy release must be able to overcome this decaying influence, or rather this must be equal to this for the case when the detonation should be formed, because what should happen? Let me again go back to the board. I have some energy which is deposited in a particular explosive gas. I am forming a shock wave. Because of this energy which is liberated, if there is no chemical reactions occurring, the Mach number of the shock front which is formed as distance moves will keep decaying. What does the chemical energy do? We did this calculation. Now, we have put an induction time, a time for chemical reactions. We say it takes place after a particular time over here. This we called as delta in our particular slide which we saw. What it does is it sort of overcomes this decaying influence and tries to push it forward at constant velocity. All what we are saying is the chemical energy release must be able to overcome the decaying influence and make it into a steady propagating front at a given detonation velocity. And this is the requirement, and therefore, we say, well, the chemical energy release must be able to dominate over the decaying influence and drive a detonation, and therefore, coming back to the slide, we say, well, the source energy term must be equal to this for the critical condition. Well, the critical condition is instead of 0 to Rs, now I say, well, Rs star is the detonation kernel, delta is the induction time or induction distance behind it. Therefore, I have 1 minus delta over Rs star into the same, you will recall this is the density ratio, this is R by Rs over here, and therefore, I can write this expression as Q into 1 minus delta over Rs divided by Rs cubed into Q plus 3. What was Q? You will recall we said that the density ratio behind the density ratio behind a blast wave, let us again go back. You had a shock front over here. We said, well, At the front what happens? You have the initial density is rho 0 in the unburnt medium over here. You have the density increase to rho s, and the value of rho s was gamma plus 1 divided by gamma minus 1 for a strong shock. For a weaker shock, well, I have 2 over ms square over here. And what happened? It decayed down. We got the slope of this. We said rho within this blast wave divided by the value of rho s is equal to, we had r, that is at any distance divided by rs was equal to q. We found out q is a large number around 15. Most of the mass is concentrated at the front, and that is the value of q. And if we put this, we get, well, the equality between energy release and chemical energy release, and we are able to now get the value of Rs star. And from that, if we calculate the value of the energy required, we find that for a stoichiometric mixture of acetylene and oxygen is between 0.5 to 3 joules depending on the pressure. At atmospheric pressure, it is around 2 joules or so. For hydrogen oxygen mixture, it is around 3 joules, maybe the variations is between 0.5 to 3 joules. For stoichiometric propane and oxygen, the energy required is around 100 joules for stoichiometric propane with oxygen. If I consider air, it is very much higher, but we found whenever we talk in terms of propane air mixture, for the energy required to start a flame was only 1 millijoule, whereas in this case it is several kilojoules, because here I am talking in terms of propane oxygen. For propane air, as I said, it is much higher, and therefore, the energy is of the order of 100 kilojoules for propane air, and therefore, we find that the amount of energy required to start a detonation is way above the energy required to start a flame. Having said that, I just show in this particular table the energy required to start a detonation in hydrogen oxygen mixture. We said around 6 joules. Hydrogen air, compared to 6 joules, you require 3 kilojoules because of the inert effects. The thing is that the induction times are larger, and that is why it becomes 3 kilojoules. Well, 3 kilojoules compares with something like 0.018 millijoules for the flame. When we talk of acetylene oxygen, 5 joules. When we talk of acetylene air, it is around 200 joules. When we talk in terms of methane oxygen, the energy required is around 100 joules, while with methane air, the energy required is something like 100,000 kilojoules, which means we are telling that to start a detonation, we require extremely large values of energy. The question is, well, that means we have said, yes, we have formulated a theory. Let's go back and take a look at what we have said so far. Yes, we have understood what a detonation is. We also know, yes, the energy required to start a detonation, that is E0 joules, is very much larger, because I need a larger kernel of detonation compared to a small quenching thickness kernel for a flame, and E0 is something like almost like 10 to the power 4 times, in several cases 10 to the power 4 to 10 to the power 6 times what is required to start a flame. Therefore, immediately we will say, well, to start a detonation in a gas is going to be very difficult. Well, it need not be so. We will see that. But the point made is, if I have to start a shock wave and form a detonation, I require larger energy release. This is true not only for explosive gas mixtures, it is also true for explosives, like let us say any explosive substances which we will study after 3 or 4 classes, like solid explosives, maybe liquid explosives. The energy required to directly form are larger, because what we require is to be able to form a shock wave which should couple with the chemical reactions. But this, as I said, need not be possible, because in practice, the type of sparks we get in accidental cases are maybe small millijoules of energy, and if I have something like an explosive gas over here, it is more likely to form a flame and not really a detonation. But then let us take another look at some of the results. We are taking a look. If I have something like gas which is flowing in a medium, and say in this particular case, I just consider, let us say a gas flowing through a particular hole over here. When it flows over here, some vortex is formed, something like a starting vortex is formed, something like like a shape over here, something like a mushroom shape is formed, and such starting vortex have been widely dealt with in literature, such as this particular author, he published a paper in Physics of Fluids on the starting vortex. But what I want to say is, whenever I have a flame, let us say I have a flame in a mixture, that means I have a pipeline over here, I have a gas mixture, I form a flame which travels slowly. You know, the flame is like a piston, and when I have a flame, it pushes the gases ahead of it, and the gases therefore acquire a velocity. That means the unburned mixture ahead of a flame gets a velocity, and if the flame becomes turbulent, it moves at higher speed, and the gas ahead of the flame which is unburned moves at high velocity. And in fact, if I have some blockages or surface roughness on the walls, what is going to happen? This high subsonic flow speed will create expansion waves, because the flow becomes sonic due to the expansion of the gases behind the blockage, and I have expansion waves which get reflected. I have something like a recirculation zone, maybe a vortex is formed over here. I have a shear layer which separates the zone of separation from the free stream zone. The expansion waves come and reflect on the shear layer, and since the impedance over here is or the mechanical impedance of the separated layer is less than the impedance of the air of the gas which is already processed, or the free stream flow of gases, the expansion waves get reflected as compression waves. See, we saw this, you remember, we had the Z value, we talked of gases moving into a higher impedance medium, a lower impedance medium. In a lower impedance medium, the compression waves reflect as expansion waves, the expansion waves reflect as compression waves, and these expansion waves merge together and form a shock wave. That means they form a shock pattern, and behind this, therefore, you have all these multiple shock structures taking place, and because these are all not, these could be either a Mach stem shock, we will consider this in the next class, and we also have maybe oblique shocks, and because of this, the flow becomes extremely turbulent ahead of the flame itself. Now, similarly, I show a Schlieren picture. You have a blockage here, you have the gases flowing. Well, you have the shock waves which are being formed, you have a shock wave at the wall, you have the reflected shock wave over here, an incident shock wave, you have a reflected shock wave, you have either it could be a regular reflection, it could be a Mach type of reflection. Therefore, you have all these shocks which are possible, and these things, what they do is they create high intensity turbulence, because you have flow directions being changing, you have slip streams over here, you have very high intensity turbulence over here, and this high intensity turbulence and also the length scale of turbulence also increases behind the lead shock wave which is in the unburned gases. Therefore, you form a very high turbulent flame which further pushes the gas at high velocity, and since you have the length scale of turbulence which is large, you have the flame which is engulfing the unburned gases, and when you have the flame which is engulfing the unburned gases, it sort of implodes, or it sort of crumbles together, it cavitates sort of, and energy is released, and this energy release could form a shock wave, and then I could have a detonation. Therefore, we say, well, this is what happens. I have the gas which is flowing, I have the turbulent structure which is being formed, it becomes highly turbulent ahead of it, and ultimately I have something like a zone of unburned gases which is enclosed by a particular shock wave, and this shock wave implodes, and this thing generates a strong shock wave which can now couple with the chemical reactions to form what we call as a detonation wave. Therefore, we tell ourselves, well, it is also possible for us to think in terms of a situation wherein I form a flame, and this flame becomes highly corrugated, and ahead of the flame in the unburned gas mixture, I have maybe the velocities are high, and as it becomes more and more turbulent, this flame becomes more and more corrugated until maybe it forms, it is able to engulf the unburned gases, and when these unburned gases they auto explode, I generate a shock wave, and now the chemical reactions take place behind this shock wave because it is quite strong, and I get a detonation. Therefore, the formation of a detonation could be from two sources, namely the direct formation of a blast wave which couples with chemical reactions. Therefore, I say, well, a detonation can be formed by directly from the ignition source, which forms a strong blast wave, which I call as direct initiation, or I could also form, in which case I could form a flame, and the flame pushes the unburned gases ahead of it, forms a turbulent gas mixture in which a turbulent flame is formed. The turbulent flame can travel at high speeds, it forms a very turbulent flame brush, and this brush, if it is able to engulf some gases, well, it forms a shock wave, and then this shock wave forms a detonation, in which case it is an indirect way of forming a detonation, which we call as deflagration. Another word used for flame is deflagration. That means a constant pressure flame, or a pressure slightly reduces across a flame, we call flame as a deflagration to detonation transition. And this is abbreviated as DDT. Therefore, two ways of forming a detonation is direct initiation. We found that the energy releases are rather high, we know how to calculate the energy release, but in this case I have a flame which forms a detonation, and the distance required from the energy release source, initially I form a flame, then after some distance I form this, the distance required is called as the run up distance. And most of the accidental explosions or explosions which occur with solid explosives, with liquid explosives, with gaseous mixtures are from flame transiting to this, and we will discuss this maybe in the next class again. To summarize then, I would like to say the following. Well, this shows the streak picture. Initially I have the flame moving over here, low velocity. Over here the conditions for detonation are formed. Well, a detonation propagates at constant velocity thereafter. And to just sum up, well, the run up distance is for deflagration to detonation transition. It is different from direct initiation, wherein the energy source formed directly at detonation, the initiation source forms the flame, which later transits to a detonation. And in most of the explosive gas mixtures, like you remember we talked of this, in a particular factory, there was an accidental leakage of propane gas. It formed a propane gas mixture. This was in Wisconsin, and what happened is this propane gas mixture interacted with the a flame got formed. The flame pushed the gases ahead of it, and the gases which were travelling at some velocity interacted with the machines in this particular machining facility. That means you have the lathe machine, it acted as an obstruction or a blockage. The gases ahead of it moved towards the particular blockage, and it created conditions wherein a turbulent flame got formed, further high velocity gases got formed, and gradually a very turbulent flame got formed. Ultimately it transited into a detonation. We will consider some cases in the next class, and what we do in the next class is therefore, we will see, yes, we have learned something about detonation, about how to start a detonation, the two methods of forming a detonation, and what we should be looking at is at the structure of a detonation. We will see it is not so beautiful, it is not one dimensional, it is a multi-dimensional detonation, and then we will take a look at some theories of detonation. Well, thank you.